Namaste. This is Vinay Kumar from Indian Institute of Remote Sensing. Today I am going to talk about Earth observation sensors and platforms. So, how we are observing Earth and we are collecting data from the sensors, and which kind of platforms are being used for acquiring the satellite data from Earth's surface. So, you already are aware of the definition of remote sensing. Remote sensing is what? It is art, science, technology of observing an object, seeing or phenomenon by instrument-based technique. So, remote means what? Because we are observing the particular object with a far distance and without being in physical contact with the object. And sensing is what we are sensing? We are sensing the electromagnetic energy either in form of reflected energy or in form of backscattered energy or emitted energy. So we are sensing electromagnetic energy remotely, and we are acquiring information from the earth surface. Now, how it came into picture and how this is going to help for extracting information from earth surface. Now, normally we know that even human beings are also equipped with remote sensing sensors. Like our eyes are seeing the or capturing the information with a far distance without being in physical contact. So, but it is having a limitation that our eyes are working in the wavelength range from visible only in the visible region. But remote sensing sensor is enabling to observe the Earth's surface beyond human capability. Means it can capture the data in the wavelength region of infrared, in the wavelength region of microwave, in the wavelength region of thermal. So whatever wavelength range could not be captured through your eyes can be captured through your different remote sensing sensors. So this is the entire remote sensing process. So in this case, you know that energy source, sensor, satellite, communication satellite, your earth surface, ground receiving and processing station. So these are the few of the things which are required. Now you can see here what is actually happening here is we have energy source. So from energy source, electromagnetic energy is coming to the earth surface and it is interacting with the target. So what is happening here is some of the electromagnetic energy is getting absorbed, some are getting transmitted, and rest of the electromagnetic energy which cannot be eaten by your targets or the material, they get reflected or backscattered to the sensor placed on the satellite. Now, in between that, you can see there is whatever energy we are expecting to come from sun or whatever energy we are expecting to go to the sensor placed on satellite, it is not going. Why? Because in between that, there is atmosphere. So because of atmospheric attenuation, there are some of the data sets which are getting lost. So these are contributing some kind of errors, and these errors needs to be corrected. Now, here another stage is whatever data sets are acquired, they are converted in form of digital number, and then it is converted in form of electronic signal, and it is transmitted to ground receiving and processing station. So in this case, you can see I have written ground receiving and processing station. Processing station, why? Because whatever data sets we have received in form of electronic signal, it is converted in form of two-dimensional image. But as I told, in between that atmosphere is there. So this type of errors which gets introduced during the acquisition, and even your sensor which is placed on satellite are also having some problem while acquiring the data. So these errors we need to fix before giving it to the user. So we have to pre-process the data, we have to do certain kind of radiometric error correction, sensor error correction, and then after we are giving it to the user for further analysis. And in between that, suppose we require some of the data on an urgent basis. Now here your communication satellite plays a role. It means you can say sometimes whenever the satellite which is not in the range of ground receiving antenna and you require data, then it passes the data to some nearby communication satellite, and from that communication satellite, the data is transferred to the ground receiving stations. So after getting the data, after fixing the errors, then the users are getting the data. We are analyzing it and we are using it for various applications, like for generating land use map, for atmospheric application, for geological application, agriculture, forestry, or disaster management. So for those purposes, we are using. Now, in this case, as I told, that whenever it is in the range of the antenna, it is transmitting the data. So you can see in this particular screen, as satellite is moving, you can see this antenna is also moving, and the electronic signal is received and it is converted in form of two-dimensional image. Now, in case of our India, we have 4 ground receiving antennas placed at Saad Nagar, Hyderabad. So here we are receiving the data, which is in the center name is National Remote Sensing Center, which is taking care of the data reception. Now coming to the definition of sensors and platforms. So whenever we are combining both the two sensors and platforms, we are able to create the image data of your Earth's surface. Sensors are what? A device which records electromagnetic energy. As I told, it may be your reflected energy, it may be backscattered energy, it may be your emitted energy. That depends that which kind of sensor we are using, either optical sensor, thermal sensor, or microwave sensor. Then coming to the platforms. So platforms are carrier bed used to carry a sensor. So normally whenever we are using even simple camera, we have to keep it in a stable platform. Otherwise, what will happen if suppose you are using a camera and you are putting in a hand and you are moving, you will not be able to get a proper information. So what you have to do, you have to keep it stable to take a proper picture of any particular area or any particular object. So platforms are required to put the sensor in a stable way so that you can capture the information in a proper manner. Now, how the remote sensing evolved? It evolved with the invention of camera. In 1827, first photograph was taken. Now you can see there are various types of platforms are used. Like in 1858, people were using hot air balloon to taking the photograph. So balloon photography was used in American Civil War. Then in 1888, rocket cameras were used. In 1903, pigeon-mounted cameras were patented. So you can see here how the cameras are mounted on the pigeon, and this is the pigeon photograph. You can see the wings in this particular photograph also. Then photograph from a kite was taken in 1906, and when the aircraft was invented, so during World War I and II, this type of plane mounted cameras were used. So this type of technology are still being used for capturing the information, because it is a low heighted platform compared to a satellite, which gives high resolution images. And whenever you require data on an urgent basis, so flying the aircraft and taking the photograph is the only easiest option. Nowadays we have UAV cameras. So from drone or UAV we can fly and we can capture the data. So after that, in 1956, U-2 spy planes were made. In 1957, first satellite was launched. In 1960, first meteorological satellite was launched. In 1967, the major technological development happened in remote sensing in terms of your satellite program, that was named as NASA Earth Resource Technology Satellite Program. So first satellite which was used for remote sensing data acquisition was IIRS, but when they launched the series of satellite, they renamed as Landsat series of satellite. So this was the first photograph taken from the Landsat. Now, out of this technology, hot air balloon and kite photography are still being used, but there are few limitations in that, because sometimes due to wind or external factors, the altitude of these platforms are not proper. So they may affect the image captured by your particular sensor. So now coming to the categories of platforms. So platforms are categorized into 3 types: ground-based, airborne, and spaceborne. Ground-based platforms are those platforms which are normally used for validating the data or for calibrating the data or whatever data captured through your satellite or airborne platform. So that can be checked through this ground-based platform. And it gives a detailed information about the Earth surface. Coming to airborne platform, normally airborne platforms are your aircraft, stable wing aircraft or helicopter. But nowadays drones are being used because that is a you can say it is a cheaper person. Means you can fly an air drone and you can capture the area, small area, and you can start doing the processing. Then coming to spaceborne platforms are your satellites. Now, what is the benefit of different types of platforms? So you can see here, when you are increasing the height of the platform, the synoptic coverage are increasing. So whenever we are using 800-kilometer altitude platform, it is covering a larger area. With a 10-kilometer aircraft, you are covering a smaller area. With hot air balloon or your drone, you can capture a smaller area. But height is one of the important factor for providing the good resolution data. If your height is low, your spatial resolution will be better. That depends upon the sensor also. But nowadays we have technique to get high spatial resolution through space technique also. So I'll be talking about that in my upcoming slide. Now, this I already told that ground-based platforms are used to record detailed information, and it is used to better characterize the target. So normally it is based on the ladder, scaffolding, tall building, or crane. Coming to airborne platform. So in this case, there are few limitations and advantages. Like suppose you require data on an urgent basis, suppose somewhere disaster happened, you can fly the aircraft and you can capture the images of the area to provide the help. And in case of this particular technology, you can use the data only when this aircraft lands. Secondly, if you want a temporal data, means if you want to get the data again and again for the area, it is not economical. It is kind of costlier operation. But in case of satellite, once you will launch the satellite, till its lifetime, it will provide you the data. So that's why satellite is economical than this aircraft thing. Now coming to spaceborne platforms. Spaceborne platforms are categorized into two things: space shuttle and satellite. Space shuttle are what? That is called as manned spacecraft, means man can sit in that space shuttle, can go to the space, can capture the information and can come back. Satellites are more commonly being used, which are once launched, it will revolve around your Earth surface and capture the Earth data. So normally satellite name was given by Kepler. When he was observing Jupiter, he found that something is guarding that particular planet. So whatever moons, or you can say Jupiter planets, natural planets are revolving around that, they are named as satellite. So in Jupiter planet, I think there are 4 moons or whatever objects are revolving around that. So he told that the name in his language, it was given as satellite. It is something like which is guarding that particular. It is a kind of guardian of that particular object. So moon is a natural satellite in our case of Earth, whereas man-made satellite include those platforms launched for remote sensing, communication and telemetry purposes. Now coming to the orbit, normally the path followed by the satellite is called orbit, and satellite moves as per Kepler's law. So by following this Kepler's law, whatever satellites are launched, they are following this 3 Kepler's law. So first law is what? The path followed by each planet is an ellipse, where sun is one of the focus. Second law is what? The line joining to the planet to sun sweeps out equal areas in equal interval of time. So means if suppose it is A1 area, it is taking time T1, and it is A2 area and it is taking time T2. So the product is always going to be constant. Third law is square of period of planet is proportional to cube of semi-major axis. So if suppose this is the semi-major axis, so if it is taking time T to complete one revolution, so square of that time period is proportional to the cube of semi-major axis. Now coming to different satellite orbital characteristics. So altitude is what? you can say from whatever satellite or sensor which is placed on airborne or satellite platform. So from mean sea level of your Earth surface, the distance from mean sea level of your Earth surface to that particular sensor, that is called as altitude. And depending on altitude, the satellites are different types of satellites are characterized, which I'll talk about. Then coming to inclination angle. Inclination angle is what? If suppose this is Earth and there is a equatorial plane and satellite is revolving with certain angle. So the angle between that orbital plane and equatorial plane is called as inclination angle. Period is time taken to complete one revolution for your Earth surface. Means suppose Earth is rotating and satellite is moving from North Pole to South Pole. So time taken to complete one revolution is called as time period. Now coming to repeat cycle. Repeat cycle means what? Like Earth is continuously rotating from west to east and satellite is revolving from North Pole to South Pole. So when Earth is rotating, after some days, satellite is revolving from the same orbital coverage or orbital path, then that is called as repeat cycle. Means revisiting of the same area by making the same orbital path. Now coming to swath. Swath is like suppose you are using a camera and camera can see to a certain width. So in this case, you can see the width seen by your particular sensor placed on satellite, that is called as swath width. Now coming to ascending pass and descending pass. Ascending pass is actually whenever satellite is moving from North Pole to South Pole, then that is called as descending pass, and whenever it is moving from South Pole to North Pole, that is called as ascending pass. So normally what happens is whenever it is moving from North Pole to South Pole, sun is looking to that area. So normally most of your optical sensor is working during the descending pass. So but your microwave sensor and your thermal sensor can work during ascending pass also, because whatever energy gets absorbed during daytime, during nighttime it will emit. So that also gets captured through thermal sensor. So but your optical sensor, which is working in the range of visible to near infrared to short wave infrared, can work during descending pass because it requires sun's energy and it is receiving the reflected energy. Now coming to perigee and apogee. Perigee is called as the closest point of the satellite to your Earth surface. Apogee is the farthest point of the satellite with your Earth surface. Now coming to altitude, as I told, altitude is categorized into three types: low Earth orbit means the satellites, and near Earth orbit satellite, and geostationary. So low Earth orbit means altitude which is with 150 to 300 kilometers altitude, which are your spy satellites or space shuttle. Near Earth orbit are altitude from 300 to 6400 kilometers. So most satellite, remote sensing satellite, which are used for Earth observation, they are near Earth orbit. Geostationary satellite, which is with 36,000 kilometer altitude above the equator. So it actually being used for weather forecasting and monitoring purposes, communication purposes. So they are actually able to view around 45% of the Earth surface. So equal geometry for each image. Now inclination angle, that angle between orbital plane and equator determines which latitudes can be viewed. Now why this is important? Because suppose Earth is rotating and satellite is revolving. Suppose it is making 60-degree angle. So till plus 60-degree latitude until minus 60-degree latitude, the data will be captured. But what about the remaining portion? So for remaining portion, normally we want our satellite should be near to the pole so that we can cover the entire Earth. Now period and repeat cycle, I already told. Time to complete one full orbit. Repeat cycle, time between two successive identical orbit. But revisit time can be do by two ways. One, as I told, by making the same orbital path. Second, by tilting the sensor placed on the satellite and revisiting the same area. Suppose you have passed from that area, means sensor had passed from this area. Now we tilted the sensor and we can revisit the same area. Now, as I told that there are different types of satellites, as I told, near Earth orbit satellite and geostationary orbit. So here you can see on the basis of that, the satellites are mostly categorized into two, geostationary and sun synchronous. Geostationary satellite is having altitude of around 36,000 kilometers. It's not fixed, it's just example. They may vary from 35,000, 34,000, and something like that, but it is around 36,000 kilometers. Orbital inclination will be 0 degree for this. Period of orbit 24 hours, because it moves with such speed that it completes the data with one Earth rotation. Then global coverage requires several geostationary satellites. Means suppose your Earth is there and your satellite is looking to the Earth's surface. So what about the remaining portion? So satellite is launched as such in different positions so that it can cover entire Earth. So this is good for repetitive observation because it is continuously seeing that same area, but poor for spatially detailed data. Why it is poor? Because your height is one of the factor which is playing a role for spatial resolution, which I'll talk about. So that's why spatial resolution is poor here. Large distortions at high latitudes, because you know that your Earth is not flat, it is somehow a kind of spheroid structure is there. So at the higher latitudes, it can have Earth distortions, means Earth curvature is included. So that's why distortions are getting included. All these satellites are west to east orbiting because your satellite Earth is also rotating from west to east. Mainly used for communication and meteorological purposes. Examples are GOES, Meteosat, INSAT, and GSAT series satellite. Coming to sun synchronous satellite, most of your remote sensing satellites are going to have this kind of altitude, 700 to 800, but these are examples. It may vary from 600 to 900, 1000, and so on. Orbit inclination will be near to the pole, and orbital period is around 90 minutes for this kind of altitude. Then sun synchronous, the name of these satellites can be sun synchronous, near polar, or near circular. Satellite orbit, as I told, it will be fixed from North Pole to South Pole, and Earth rotates beneath it. So because of the rotation of this Earth and revolution of this satellite, entire Earth data gets captured. Normally, it crosses the equator at morning time. So that, as I told, it is working during descending path. So whenever it is moving from North Pole to South Pole, so during daytime it is passing, so that the sun illumination should be there. That's why it is also called as sun synchronous. It is synchronized with the sun's energy. Now satellite orbital plane is near polar, and the altitude is such that satellite passes each place at same local sun time. Okay. Now it covers entire globe. Examples are your Landsat, Spot, Sentinel, IRS, RISAT, even ALOS. There are many satellites from different space agencies. So you can see this particular above animation, how that Earth is getting rotated, and because of the rotation of Earth and satellite is Earth is rotating and satellite is revolving from North to South Pole, it is covering the entire Earth data. Now I'll show you the example of SWAT, how SWAT is capturing the data, and what is SWAT and how that is working. So you can understand this particular image. By seeing this image, you can see this is particular sensor which is revolving around Earth, and how much area is getting captured through your particular sensor. So because of this, that particular width is getting captured, and it is revolving from North Pole to South Pole. Now I'll show you another example. You can see. So you can see that how the data is getting captured through your sensor, and how the satellite is scanning the Earth, and it is moving from North Pole to South Pole. Okay. Now, next is I'll be talking about different types of sensors. So as I told about ascending pass and descending pass, so normally sensors, remote sensing sensors are dependent on external source of energy or own source of energy. So there are two types of sensors. They are called as passive sensor and active sensor. Passive sensors are what? Which is dependent on sun, like sun is sending the energy and reflected energy is getting recorded by your sensor. Active sensors are those which is sending the energy, and back scattered energy is going to the sensor. So they are your microwave sensor or your SAR sensor. Lidar sensor is also the same, your active sensor. Uh, so it can work during daytime only, passive sensor, but active sensor can work at, means it is independent of time, means during day and night both can it can work. But thermal sensor is one of the passive sensor which can work at night also. Now, depending on that, your sensors are categorized into two types, imaging and non-imaging sensors. Non-imaging sensors are passive and active. So in that case, like spectroradiometer is one of the instrument which is normally used for measuring, or you can say spectral reflectance curve of any particular target. Means wavelength versus the reflectance value is measured by your spectroradiometer. Active sensors, in case of non-imaging, they are laser distance meter, laser water depth meter, microwave altimeter. So for measuring sea depth or lake or something like that. So for that, if you have to measure the depth, then this type of instruments are used. Laser distance meter also being used for measuring the distance. In this case, they are working with the principle of by focusing to the particular target, and laser pulses are sent and it is received back by the sensor. So by calculating the two-way travel time, the distances are measured in all these cases. Now coming to the imaging sensors. So normally imaging sensors are also categorized into passive and active. So your normal photographic camera can, whenever we are using external source of energy, they are your passive sensor. But when it is using flash for capturing the data, they are active sensor. So optical scanners. So most of your remote sensing sensor are using this two technology, across track and along track, for capturing the data. And then thermal scanner is also there. Active sensors are your SAR sensor, which is using microwave wavelength region. This is using infrared wavelength region, that LiDAR. So SAR sensor can penetrate through clouds also because of the longer wavelength region. And LiDAR sensor are able to give you the X, Y, and Z information, and using that you can generate the digital terrain models. Now, coming to the cross-track multispectral scanning, they are also called as whisk broom scanning. It is working in the principle, like here you can see there is a swath. So in this swath it have to capture. So it is working with a detector with a rotating scan mirror. So across the track, it is collecting data pixel by pixel in a series of lines and moving in further direction. So you can see here that how the rotating scan mirror is moving and how the images are getting captured for this area. Now, the lines are oriented perpendicular to the direction of motion of sensor platform, and data are collected within an arc below the system, typically of some 90 degrees to 120 degrees. So it means the field of view is varying from 90 degrees to 120 degrees, and the detector, whatever is seeing, that is the angle it is making, solid angle, that is called as instantaneous field of view. Okay. Now the examples of these sensors are multispectral scanner, thematic mapper, and operational land imager of your Landsat series of satellite. AVHRR of NOAA satellites are example of whisk broom scanners. Now, why it is called as whisk broom scanner? It is something like you are using a broom and you are sweeping the floor in this particular manner across the track and collecting the data. That's why it is called as whisk broom scanning. Now coming to the another type of scanner, that is called as along track multispectral scanner. Now in this along track multispectral scanner, in place of single detector for a single band, here we are having a linear array of detectors. That is called as CCDs, small charge coupled devices. Small detectors are there, which are placed in a linear array, and they are moving as if like we are pushing the broom in further direction and scanning. Now, the limitation of across track is what? It have to collect data pixel by pixel, but it have to move until that satellite is also moving in which it is placed. So what is happening, whenever it reaches to the extreme, there is a kind of one pixel shift or around shifting of that particular pixel when it reaches to the extreme. But in case of push broom or along track scanner, when it is moving along the track, it is capturing the data and it is moving with the particular platform. So that kind of shifting in the pixel data acquisition will not happen here. Examples of this particular long track scanners are RIS and wide field sensor of Indian remote sensing satellite series, and spot series sensors are also example of push-broom. Now, what is the advantages and limitations that I'm going to talk? You can see a cross-track scanner. If suppose you will see that this is the 90-degree field of view and the swath width is 20 kilometer. So same swath width we are also taking for a long track scanner. Now pixel size is 10 meter by 10 meter. Here also pixel size is 10 meter. Now the scan rate of rotating mirror is 2 into 10 to the power minus 2 second per scan line. So we can calculate the dwell time. Dwell time means up to what time it is seeing the Earth's surface. So why it is important? Because if you are going to look over an object for a longer duration, you are receiving more signal. So you will be able to get more interpretable information. Like simply you are using your camera, and suppose you have taken the camera, you click the photograph. But sometimes you are adjusting the camera, you are putting it stable, you are focusing it properly, then you will get better information. So dwell time is important here. So scan rate per line by number of cells per line. So in case of 20 kilometer swath and 10 meter spatial resolution, there are 2000 cells. So if you calculate that, scan rate per line is 2 into 10 to the power minus 2 second per scan line by 2000 cells. The dwell time is 1 into 10 to the power minus 5 second per cell. Now coming to this dwell time of this long track scanner, cell dimension is what? 10 meter per cell. Velocity of this satellite or platform is 200 meter per second. So the dwell time here is 5 into 10 to the power minus 2 second per cell. So longer the dwell time, better is the, means you can say stronger signal is received by the detector, and you can get a better resolution data in this particular case. But there are few limitations also with the long track scanner, because we have thousands of detectors placed in a linear array. So sometimes cross calibrating the detectors are difficult. But in case of whisk-broom scanner, you have a single detector. So some advantages are there with whisk-broom scanner also. Some advantages are there with the push-broom scanner also. Now, coming to high resolution imaging mode, as I told, nowadays satellites are space-bound platforms are giving very, very high spatial resolution. So in place of linear array of detector, we are using area array of detectors. Means we have n number of arrays placed in a rows, a different, you can see in this particular thing that how the arrays are placed. Now it captured first row detector have captured the data, then it moved further, then second row detector have captured the data, then it moved further, then third one. So like that, you can see more signal have was received from the same area, and the signals were integrated and the information were extracted. So same thing here also, you can see that single line, dual line, and with the different n number of arrays we have collected. This is called as time delay and integration. So IIRS satellite sensors are working on this principle. Coming to our Cartosat series satellite, step and stare technology are being used. Step and stare means, like suppose this object have to be looked, and here it is starting with a particular position at time, start time is this A and end time is B. So it is moving at different steps and staring to the same place. So this moving from A to B, it is receiving the signal from the same area. So that's those signals were combined and integrated, and we are giving it to the, means we are getting stronger signal for that particular area for getting high resolution data sets. Now coming to, first we have to understand what is digital image. Normally what happens is whenever we are zooming any photograph, we zoom it. What is happening? It is getting pixelated. Okay, so small unit of that particular digital image is called as picture element, and short form of that picture element is called as pixel. Now you can see each and every particular object has different reflectance value at different wavelength. So like normally the features which absorbs most of the energy will appear darker, means which is not reflecting back much. Which is reflecting back more, it is having highest reflectance value, it will appear brighter. So like that. So you can see here when you are normally trying to, sometimes you are using digital photograph, you are trying to enhance it, you are trying to change the value, trying to play with, like you are enhancing it. So how we can do that? Because your digital image is nothing but some numbers are there, and your computer is seeing those numbers. As I told, darker features will reflect less, your brighter features will reflect more. So these numbers we are playing with for getting the more interpretable information. Now, depending on the basis of that, you can say that resolutions are categorized into 4 types. Means the pixel size, whatever I told, the pixels, whatever I told, the size of the pixel will talk about spatial resolution. The value in the pixel will talk about radiometric resolution. And when it is different bands like blue, green, red, near infrared bands are captured, we will talk about spectral resolution. And how frequently we are observing the same area, that is called your temporal resolution. So you can see the resolution definition: ability of a system to render the discretely separable quantity in terms of distance, wavelength, time, and radiation. So it means spatial means, suppose we have two objects with 1 meter apart, and your pixel size is 10 meter. So these two objects will come in a single pixel, we will not be able to distinguish. But if your pixel size or your spatial resolution is 0.5 meter or 1 meter also, these two different objects may appear at two different pixels. So we will be able to distinguish it. So that's why it is called as measure of discernible physical dimension on the surface of Earth. Spectral resolution is what? Normally, if you have like black and white camera and RGB camera, what is the difference? In case of black and white camera, you are able to differentiate on the basis of different gray colors. Like black means which is having lowest reflectance value, bright means which is having highest reflectance value. But if you have different bands and using that you can plot a spectral reflectance curve, then you will be able to differentiate the features in a more detailed way. Means you can identify the features, like if suppose you have a high spectral resolution data, even different vegetation species you can differentiate. Coming to radiometric resolution, it is means whatever minimum energy level it's recorded by your sensor, that is your radiometric resolution. So I'll talk one by one. Coming to spatial resolution, as I told, physical dimension on Earth is recorded. It refers to the amount of detail that can be detected by your sensor. So detailed mapping requires greater spatial resolution. So you can see here, this is the pixel dimension. This is the IFOV. IFOV is the solid angle made by your sensor. And this is your ground resolution element, which is we are talking about, which is your spatial resolution kind of. You can say instantaneous field of view, the solid angle through which a detector is seen, and this is dependent on detector dimension upon focal length. Ground resolution element is what? Instantaneous field of view, and whenever you will multiply with the height, it will tell you the ground resolution element. So as I told, height is very important. So that's why your geostationary satellites have a poor or coarser resolution. So height is playing a role over here. Now coming to information content versus resolution, you can see this is an example of ocean color monitor data. And when we took the area of around 4 kilometer by 4 kilometer, you can see we are unable to interpret the features over here. But when we took 188 meter resolution data, we started seeing certain information, but not clear. Now you can see with a 72 meter resolution list 3 data, we are started seeing certain features, but still not clear. Then coming to 36 meter resolution data, here we can tell this maybe airstrip, vegetation, urban, still not clear. Now in this case, you can see the 23 meter resolution data, more interpretable information is there, but the shape of the features are not clear. But when we took 6 meter panchromatic data, we are able to see the detailed features. But panchromatic data are the sensors, which is a single band data, and which is using wavelength range, either visible or visible to near infrared range for capturing the data. This particular sensors are multispectral data with different bands, and they are generated as color composites. Now coming to This another example, AWIFS data with 56-meter resolution, 30-meter resolution, then 23-meter resolution, 50-meter resolution, 6-meter, and ICONOS resolution. So you can see similar areas were taken. The features were not in, but when we went to higher spatial resolution, you can see this agriculture fields are clear. But here you can see with 4-meter resolution data, we can clearly differentiate the features. But shape of the buildings are still not clear. But with 1-meter data, you can see these buildings are very, very clear. So for which application, which kind of satellite data are being used? For meteorological application, you require very coarse resolution. For oceanographic, ocean color monitoring, you require around 300 to 1 kilometer resolution. For land use mapping, you require 20 to 30-meter resolution, like crop monitoring, forest mapping, hydrology. Cartography and urban planning require 2 to 6 meter, and for military surveillance, less than equals to 1 meter resolution data is required. Now coming to spectral resolution, as I told to you that what is the difference between panchromatic and multispectral. So here you can see when we are increasing the number of bands, what is happening here. So here we have 6 multispectral bands. When we plotted the spectral profile or spectral reflectance curve of a feature, you can see this is telling the nature of the feature. This is vegetation. When we increase the number of bands here to 9, this sensor is having 9 multispectral bands, we started seeing certain kind of absorption. And when we use hyperspectral bands, which is 150 after processing, you can see the smallest absorptions are visible. So which separates the different vegetation species which with each other by seeing this particular type of spectral feature. So high spectral resolution, better ability to exploit differences in the spectral signature. So here spectral resolution is what? It describes the ability of sensor to define fine wavelength intervals. Now, in this case, you can see when we have different multispectral data, this is a Landsat satellite data example, which is having 6 multispectral bands. 6th band is actually thermal band, so that's why it is not mentioned. So with that bands, we can generate true color composite or natural color composite. So when you visualize red band through red color gun, green band through green, and blue through blue, that is called as true color or natural color composite. But when you visualize near infrared band through red, red band through green, and blue band through blue, then that is called as standard false color composite. Now, why we use this kind of color composite for interpreting the information? Because you know that shorter wavelength scatters more, like blue wavelength scatters more, and near infrared bands have high reflectance in case of vegetation. So that's why for differentiating water and vegetation cover, this particular band combination is best for interpreting the features. Now you can see for different bands have different application, like your blue band is used for penetration of clear water, bathymetry, and mapping of coastal waters. For green bands used for recording the green reflectance peak of vegetation, assess plant vigor, reflectance from turbid water. Red band is used for seeing the chlorophyll absorption region and best for detecting roads and bare soil. Near infrared band is used for estimating biomass and separates water bodies and vegetation. Mid infrared or short wave infrared is actually considered as best single band for discriminating most of the features, and the longer mid infrared band is useful for discriminating mineral and rock types and for interpreting vegetation cover and moistures. Now you can see reflectance differ by wavelength. You can see this particular area, which is with green reflectance. Here vegetation is appearing darker and the urban features are brighter. But when we have to differentiate between water and vegetation, you can see water is appearing clearly dark and vegetation is appearing brighter. So this is happening because water has lower reflectance in infrared region and vegetation has higher reflectance in infrared region. Now, in this particular case, you can see cloud and snow is appearing in white color, and we have to differentiate that. So in near infrared, they are appearing brighter. But when we use short wave infrared reflectance, you can see cloud are still whiter and snow is appearing darker. So you can see here the reflectance curve of cloud is constant throughout the wavelength. But in case of snow, it is getting absorbed in the longer wavelength region. Now coming to the short wave infrared and thermal infrared band, here you can see the lava, molten lava coming out of the volcano is clearly appearing because of the high temperature, but it is not visible in the short wave infrared region. Now coming to the radiometric resolution, it describes the actual information content in the image. This is sensitive to magnitude of electromagnetic energy determines the radiometric resolution. So it actually discriminates the very slight differences in the energy. If suppose there are two features which have very small variation in the energy level recorded by the sensor, so if your radiometric resolution will be high, you can differentiate that. So how? I'll be showing that. You can see that is dependent on the number of bits. So if 1 bit data is there, 2 gray labels will be there. If 2 bit data is there, 4 gray labels. 3 bit data, your 0 to 7 means 8 gray labels. 4 bit data, you have 16 gray labels, 0 to 15. 0 is considered as dark and higher value is considered as the brightest one. So here you can see with different gray labels, 2 bit, 3 bit, 4 bit, 5, 6 and 8 bit data, you can see how the features are differentiable here. With 2 bit data, it is appearing in a 3 gray labels. In this case, you can see, or you can 0 to 3, 0, 1 to 3, 4 gray labels. In 3 bit data, you have 8 gray labels. So by looking over that, when we are increasing the gray labels, we are able to see differentiate the features in a more clearer way. So why it is required, you can see with a radiometric resolution of data, you can see when the data is used only 8-bit radiometric resolution, the shadow part is not able to provide information where the shadow is there. But when we utilize the 11-bit resolution, you can see this features beneath the shadow is now clearly visible or interpretable over here. Now coming to the temporal resolution. Temporal resolution represents the frequency with which a satellite can revisit an area and acquire a new image. As I told, that depends on two things, that how the satellite is revisiting the area, means making the same orbital coverage. Second, by tilting the sensor and revisiting the same area. So you can see here there are two images acquired during November month and February month. Here when the vegetation is healthy, how it is appearing in red color, and when the vegetation is dry, how it is appearing. So normally for different application, different temporal resolution is required. For meteorological application, hourly need is required. Oceanographic application, 2 to 3 days. For stereo viewing, 0 to 1 days of repeativity. For vegetation monitoring, 5 days of repeativity is required. Now coming to various Earth observation satellites, till now there are many satellites are being launched from different space agencies. From Europe, we have Spot series of satellite. Latest one is Spot 6 and 7 with a purpose of generating high spatial resolution data of entire Earth. From European Space Agency, we have Microwave series of satellite and Sentinel series of satellite. So Sentinel-1 is the SAR data provider, and Sentinel-2 series are providing the multispectral data with 10 meters spatial resolution. Then from Middle East, Israel, IIRS series of satellite. There are other satellites also being launched from Israel. Then from USA, we have Landsat series of satellite. And your high resolution satellite, your Iconos, GeoEye, they are from your USA. From Canada, we have RadarSat series of satellite, which is with a very SAR sensor, which is with our SAR sensor. From India, we have Indian Remote Sensing Satellite series and Cartosat series satellite. So latest Cartosat 3 was launched with 25 centimeter resolution. From Japan, we have ALOS satellite. So these are the distribution agencies which are taking care of data distribution. From India, we have National Remote Sensing Center, which is taking care of the data distribution. Now, Landsat series satellite first launched in 1972 with multispectral scanner with 80 meter resolution. Then 1, 2, 3 are the series of satellite. Then Landsat 4 was launched with an enhanced sensor, that is thematic mapper. Landsat 5 was also having similar sensor. Landsat 6 failed just after the launch. Landsat 7 was launched in 1999 with additional 15 meter panchromatic sensor. Then Landsat 8 was launched with operational land imager and thermal infrared sensor. So these are the additional thing like coastal blue bands, IRS bands were there, and 2 thermal band of 100-meter resolution. The Spot series, as I told, Spot 6 and 7 recently launched. So Spot series satellite was launched with a purpose of stereo capability. So whenever Spot satellite was launched, it is having a tilting capability. It can see revisit the same area by tilting the sensor. So from that, you can generate a 3D models from this kind of images. Now Sentinel satellite series, as I told, the Sentinel-1 is providing SAR data. Sentinel-2 is providing multispectral with 10-meter spatial resolution. Other bands are also there with coarser resolution as well, but 10-meter spatial resolution with blue, green, red, and near-infrared bands. These are there. They are also other sensors also for radiometer, ocean color monitor. Those sensors are also placed in the other Sentinel satellite series. This is the ALOS satellite series, ALOS 1 and 2. ALOS 1 was launched in 2006 and ALOS 2 was launched in 2014 with compact infrared camera and your microwave sensor camera with L-band. These are the Indian remote sensing satellite series, which started with IRS 1A, 1B, and now we are having Cartosat 2 series, which is providing very high resolution. Cartosat 3 was also recently launched. RISat 2B was also a SAR satellite, which was recently launched, and HISIS is one of the sensor, which is hyperspectral sensor, which is also recently launched. So these are the satellite sensors which are launched. IRS 1A, 1B with a 72-meter and 36-meter resolution. Then they launched WIFs and LISTRI sensor with 188-meter and 23.5-meter. ResourceSat series satellites were providing 56-meter and 5.8-meter multispectral data. Now the difference between ResourceSat 1 and 2 and 2A is what? Radiometric resolution got improved in this 2 and 2A. IRS Cartosat series satellite are with 2.5 meter, 1.8 meter, and Cartosat 2 series was with less than 1 meter in panchromatic and multispectral 2 meter. Cartosat 3 was with 1 meter and 0.25 meter for panchromatic. Now coming to hyperspectral sensors of your India. So ISRO collaborated with NASA and we have flight IIRS NG at different sites of India. So this was NASA sensor. Next generation IIRS mission was there with 5 nanometer spectral resolution. HISIS was launched from ISRO. So that is also having 60 VNIR and SWIR hyperspectral bands with 30 meters resolution with 30 kilometers swath width. And these are RISat 2, this is X-band SAR sensor, and these are the C-band SAR sensor RISat 1, and 2B is also the continuity mission of this particular sensors. Now these are few of the satellite images from different sensor, list 1, list 2. So list 1 is with 72 meter, list 2 is 36 meter resolution. So how the images features are there in this particular spatial resolution. And this is the sensor, list 1 and list 2 sensor. Now this is list 3 camera with 23 meter resolution, and this is IRS pan camera with 5.8 meter. This is the area which is Chandigarh city, the image captured for that Chandigarh city, and this is a Hyderabad city, which is the popular Hussain Sagar Lake is there. So this is the Hyderabad city and this is the Hussain Sagar Lake. This is the WIFs camera, and this WIFs camera is advanced. It is modified, and advanced wide field sensor was launched with 56 meter. Earlier it was with 188 meter resolution. So you can see southern part of India, Sri Lanka, how it is visible, the clouds and all. And this is the snow, how it is visible with your 188 meter resolution. Now this is list 3 image of 23 meter resolution. So this is of Hyderabad city of India, one of the capital of one of the state in India. So you can see the airstrip and the lake and the urban area, how it is visible over here. And this is Ahmedabad city of your with 5.8 meter resolution. So how the buildings and other features are visible with 6 meter is clearly visible here. Then this is Cartosat images. So you can see Cartosat images are single band images. So you can see how the individual buildings are detected, even vehicles are detected through this kind of resolution. The aircraft and all is visible through this kind of resolution. Now, this is the Cartosat 2 series image, fused image, panchromatic and multispectral, and true color composite images are shown. So here you can see the stadium and individual building and trees are clearly visible here. With Cartosat 3 images, you can see the vehicles parked in this near to the stadium are also clearly visible. Now, Indian Earth observation missions in the near future, ResourceSat 3 and 3A, OceanSat 3 and 3A, and RS Sampler 3S and 3SA will be launched very soon. Then coming to the high spatial resolution satellite from different countries. So first commercial satellite which gave the near photographic quality image of anywhere in the world from space was IKONOS. QuickBird, WorldView 1, 2, 3, and 4. So WorldView 4 is providing the very highest spatial resolution, this 3 and 4. GeoEye images are also providing around 40 centimeter resolution. Comset are from Korea, Korea, so they are also providing very high spatial resolution data sets. So this is one of the IKONOS image of Indian Institute of Remote Sensing. So you can see how the buildings and other features are visible over here. And these are the individual buildings and tree. This is the fused image of multispectral and panchromatic. This is GeoEye 1 image and IKONOS image before and after the disaster. So you can see here the buildings over here, and after the disaster what has changed. So you can see these buildings are getting affected in the nuclear power plant disaster. Now coming to the ComSat 3 and 3A image. So these are your high resolution images, and WorldView 3 and 4 images. You can see how individual car and the color of the cars are visible through your space. Now coming to meteorological satellite designed specifically for weather prediction and monitoring, advantages of global coverage at very high temporal resolution. NOAA series satellites are near polar, but they are used for meteorological purposes. GO, GeoSat and INSAT series satellites are in geostationary orbit. GSAT and INSAT series satellites are used for telecommunication and meteorological purposes. Now, where we should get this kind of information? So ITC have prepared a kind of database. So this website you can visit, and you can see that which satellites are launched, which satellites will be launched in future, what is the sensor specification, where you can place the data order. So those information you can go get from this. If you want to do the satellite tracking, so real-time satellite tracking, so you can visit this website. So from there you can may track some of the satellites. These are few of the data browsing websites. So from where we can browse satellite data. nrsc.gov.in is for Indian remote sensing satellite purchase and all. You can browse and you can place order. And Bhuvan is for some of the openly accessible data sets are there, where you can openly access the data. Earth Explorer is for other satellite like Landsat series of satellite data you can get from this. So these are various websites where you can browse satellite data sets and all. So thank you everyone.